Hey guys, how's it going? Welcome back to the Majestic Masiakasaurus YouTube channel. Today we're in a bit of an outdoor setting. I got a new video for us to take a look at. This one is titled How Gravity Works on the Flat Earth, which is something I've honestly been very interested in. I'm curious, like on a disc, is there gravity? Does it work the same way? I've heard a lot of different weird theories. Today we're actually going to find out together. I have seen this video before once, but it was a little while ago. I don't remember it super well, and it was mostly just me sort of skimming through to try to get an idea of what his main arguments were. So we're going to be taking a look at this today. I hope you enjoy it. I suppose just real quickly before we jump right into the video, because I'm sure many of you are new to the channel because the channel itself is quite new. My name is Milo, and I love science. I love the natural world we live in, and paleontology is one of my nerd areas of expertise, but I love science in general, so I like to take a look at some really bad science that's happening, because unfortunately there is quite a bit of that. And I do my best to try to show you guys why you should not believe everything that is on the internet. I hope not to only to show you why a lot of these ideas are bad, but why they're misinformed. So today we're going to be looking at another classic bad science idea: flat Earth. One last thing, by no means am I an astronomer or a physicist or by any means an expert in this field, but then again, neither is this guy running this video, so seems like you're going to have to judge our arguments based on their own merit and not by who's saying them. P.S. That's a good way to judge any argument, but just a reminder.
Long before the theory of gravity was a glimmer in Newton's imagination, the natural physics of density and buoyancy already perfectly explained why apples fall down. Quite simply, objects fall or rise based on their relative density to the medium surrounding them.
So yes, kind of. You're kind of already describing gravity. But first of all, I'd like to point out, we have all these different liquids that supposedly have different densities, and that's why they're forming in the way they do, which is really cool. I assume that he meant to spell dye, D-Y-E. It's not that funny, but I think it's pretty funny. Anyway, I guess what I should do is probably start by just explaining what gravity is, just basic level. Gravity is the strange force that every object exerts on every other object around it. So believe it or not, I actually am exerting a small, minuscule gravitational pull on this pencil, but it's just not very strong. It's extremely weak, and the reason that is because gravity is based on two variables: mass and distance. So the closer two objects are together and the more massive they are, the stronger the gravitational pull between those two objects. That's why we actually stay on the Earth and why everything falls when you drop it, because the Earth is so massive and we're close enough to it that its gravitational pull on us is extremely strong. So that's what essentially Eric seems to be trying to show us here in this can of different liquids of different densities. What's really happening is that each one of those liquids actually has a slightly different mass, and so the gravitational pull the Earth has on each of them is slightly different. Essentially, that's why the bolt is at the bottom, because the bolt is more massive than the ping pong ball at the top, so gravity is exerting more force on that bolt than it is the ping pong ball.
Apples fall because they are denser than the air, while helium balloons rise because they are lighter. No gravity necessary.
Yeah, except that what you are describing is actually gravity. So the reason that balloon is flying up is because the contents of that balloon, the air molecules within it, whatever they are made of, is actually less massive than the contents of the elements of the air around the balloon. So the Earth's gravity is actually pulling down more on the air, the substance that is around the balloon, than the air that is within the balloon. As a simple Google search would tell you, helium is pulled by gravity the same as everything else, but because it is pulled less than the surrounding air, the air moves downward and the helium takes its place higher up. In other words, the Earth's gravity is still acting on that helium balloon, just less so than the surrounding air. Would you please just do a little bit of research, a little bit? Seriously, one quick Google search, that's all it takes.
This is why raindrops fall down through the air, and air bubbles rise up through water. Everything seeks its relative density and rises or falls until settling accordingly. This is why a tiny pebble sinks to the bottom of the ocean, but gigantic cruise ships and aircraft carriers stay afloat on the surface. Because even though a pebble is so small, its mass relative to its volume, its density, is more than water, so it sinks.
Again, I don't think you really understand what gravity is. The issue that I'm seeming to have with this way of describing why things fall is that really you can't actually explain why. Sure, your argument is that something is more dense and that's why it falls or sinks, but my question is, why is it that an inherently denser object would fall closer to your flat Earth than a less dense object? You don't really have an explanation for why that happens. My explanation is, that's how gravity works. The reason that pebble sinks through the water is because it is actually more massive than the H2O molecules surrounding it. So the Earth's gravitational pull affects that pebble more than it does the water, therefore pulling the pebble through the water. Again, it's like you're sort of describing gravity, but then just not calling it gravity, and then not having an explanation for why it happens.
And even though a cruise ship is so large, its mass, relative to its volume, is less than water, so it floats. If Newton's apple had landed in a puddle instead of on his head, he would have seen the apple only fell through the air because it was denser than the air, but then floated on top of the water because it was less dense than water.
Ah, I see now the problem. Sir, you didn't stay in science class. And that bottom caption where it says, well, that only proves that I'm denser than the air. Well, sort of. Again, yes, you're more massive than the many molecules making up the air around you, so gravity is exerting more force on you than it is that air pulling you through it.
Have you ever noticed how it's easier to stay afloat with your lungs full of air than it is when they're empty?
Actually, yes, I have noticed that, though I would ask you the same question, because you seem pretty dense.
Submarines float on the surface when their ballast tanks are filled with air, but when the vents are opened and seawater floods in, they begin to sink as the submarine's density becomes greater than water.
Again, not to be repeating myself, but essentially what's happening here with the submarines is that when those ballast tanks fill up with air, that air is significantly less massive than the water, so it sort of counterbalances the really massive submarine, which helps it rise or sink through the water. Essentially, adding or subtracting the air from inside those ballast tanks is either increasing or decreasing the mass of the submarine, which in turn means the gravity affects the submarine differently.
Depending what depth they wish to dive, sailors simply adjust the ratio of air and water in their tanks, and when ready to resurface, they blow compressed air into the tanks, forcing the seawater out, lowering the density, and thus causing them to rise back to the surface. We can also prove this fact of relative density by filling a balloon with approximately half helium and half air. Since helium is lighter than the oxygen, nitrogen, and other gases that compose the air around us, filling a balloon with just the right amount of helium to compensate for and balance out the density of the plastic results in a gravity-defying, levitating balloon at equilibrium that neither rises nor falls.
So yeah, this is actually a pretty cool looking experiment, right? You have this balloon which essentially sits there and seems to defy gravity. Well, it does look pretty cool, but the thing is, it's not actually defying gravity. Gravity is still pulling on it. That's why it's staying there. By adding the right ratio of helium to oxygen to nitrogen or whatever else they put in that balloon, they've essentially figured out the exact right mass the balloon needs to have so that its mass is about the same as whatever the air is around it, so it is neither more dense or less dense or more massive and less massive than the air around it, so it is neither going to float or be pulled any farther. The reason this balloon is staying there is because gravity is still pulling on it. Gravity is holding it there. That's not why it's just flying around or floating around like it would in space with no reason. Gravity is holding that balloon where it is. Even though it's not actually pulling all the way down, gravity is still acting on it.
How is it that gravity is so strong that it can hold all the oceans, buildings, and people stuck to the underside of the ball Earth, but so weak that it allows birds, bugs, smoke, and balloons to casually evade its grips completely? How is it that gravity holds our bodies clung to the underside of a ball Earth, but yet we can easily raise our legs and arms, walk or jump, and feel no such constant downward pulling force?
Well, yeah, the other thing is it turns out gravity is not that hard to defy temporarily. That's why when you jump, you can actually leave the Earth, right? You're strong enough to actually defy gravity for that moment and push in the opposite direction. But then what happens after you jump? You fall again. And he mentioned this weird idea that you can lift your leg, just like I'm lifting my arm right now, so I'm defying gravity. Well, the thing, if I keep holding this here for long enough, it's going to start getting tired because gravity's pulling down on it, and I actually have to exert energy in my muscles to hold my arm up as I do this. And eventually I'm going to get tired because I'm actually battling with gravity right now, and eventually I'm going to get so tired my arm's going to fall again. The other thing that I thought was sort of strange is he mentioned, why is it that gravity can keep people clung to the underside of the Earth? So what on earth do you mean by underside of the Earth, right? You realize that in space there is no up or down, side to side, like there is no directions. There is only toward or away. That's it. So the people that are, walking through Antarctica right now, or all those penguins down there, they are just as much the underside of the Earth as where I am right now in the United States. It's just because you've seen all those maps, right, where the Antarctica is at the bottom and Canada, Russia, and the Arctic Circle are all up at the top. You could turn that map 180 degrees around and put Antarctica at the top of the map, and it would still be just as accurate. This is something that I actually see a lot with flat earthers. Is like, well, how are those people down in Australia not falling off, right? It's because it's not actually the bottom. It's just a sphere, and there is no direction up or down in space. Gravity is pulling us all toward the center of the Earth, not necessarily down. It's just down because the way we stand, we look down and that's where the Earth is.
How is it that gravity can cause planets to revolve elliptical orbits around a single center of attraction? Ellipses by nature require two foci, and the force of gravitation would have to regularly increase and decrease to keep planets in constant orbit and prevent pulling them into direct collision courses.
So the amount of gravitational pull that the Earth has on us, or the amount that I have on everything around me, doesn't actually change. So remember the two variables that change the force of gravity. Mass is one, the one we've been mainly talking about, but also distance. So this is how gravity can appear to change. If you're thinking big, like planetary size, the gravitational pull that like the sun has on, let's use Pluto for an example. So Pluto has this weird thing going on. Yeah, sure, we're gonna make this deck of playing cards the sun, okay? And this rock is Pluto, not to scale. Pluto has this weird thing going on where it has an especially ovular, is that a word? Like an oval? Anyway, not spherical orbit around the sun. So instead of circling the sun in a nice sphere like this, Pluto circles something more like that. So, the farther the Pluto gets from the sun, the gravitational pull the sun is exerting on Pluto actually is decreasing. I think I know where this idea is going in the video, but I'll let them say it and then I'll tell you what I think.
Einstein's theory of relativity and the entire heliocentric model of the universe hinge upon Newton's law of gravitation. Heliocentrists claim that the sun is the most massive object in the heavens, more massive even than the Earth.
So real quickly, the sun is not the most massive thing in all of the universe, or the heavens, as he put it. It's the most massive in our solar system, which is why everything in our solar system revolves around the sun. But astronomically speaking, the sun is actually quite small compared to many other stars out there, so it is by no means the most massive object in the heavens.
And therefore the Earth and other planets, by law, are caught up in the sun's gravity and forced to orbit perpetual circles and ellipses around it. They claim that gravity also somehow allows people, buildings, the oceans, and all of nature to exist on the underside of their ball Earth without falling off.
There's not an underside of the ball Earth. It's a sphere, and there's no up or down in space.
Now, even if gravity did exist, why would it cause both planets to orbit the sun and people to stick to the Earth? Gravity should either cause people to float in suspended circular orbits around the Earth, or it should cause the Earth to be pulled and crashed into the sun.
Alright, so here's essentially the argument they're saying. Why is it that gravity makes us stick to the Earth, but then also makes the Earth revolve or orbit the sun? We should do one or the other. Why is it doing two things at the same time?
Hi there, sorry to interrupt. Milo from the future here. Well, I realized after editing this video it was much too long to upload all in one piece, so I've chopped it into 2 videos, and congratulations, you've just finished the first half to this wild adventure. Really, in my opinion, it only gets better from here, so if the second video's already been uploaded, the first link in the description will be a link to that video. I'd recommend you go watch it. Thanks so much. But if you're watching this early and the second half is not out yet, then I would just recommend subscribing to the channel so that you'll know exactly when the second part comes out. And it should not take long, I promise. Well, thanks so much for sticking through this first half. Hope to see you later. Peace out.